In this episode, we're going to look at binary variables, learn what they are, learn how they can be used in groundwater management applications, and see some examples of this in the context of the dewater problem. So, what is a binary variable? It's distinguished from a flow and external variable, which can take continuous values within bounds. A binary variable, on the other hand, is limited to taking the value of 0 or 1. It is forced to take either one of those two values. And as we'll see, that has quite a bit of utility. Here's some definitions used in GWM. We use the variable capital I to represent a binary variable. L is the subscript to indicate which one. We say that binary variables are associated with a flow or external variable. And this means that if the binary variable is non-zero, then the flow variable can be non-zero. In other words, they're coupled together in such a way that they are either both zero or the flow variable is non-zero and the binary variable takes the value of 1. Here's an example of this. We have 3 wells, QW1, 2, 3, and let's assume that we've associated a binary variable I1 with flow variable QW1. This means if I1 is equal to 0, then QW1 is forced to take a value of 0. Alternatively, if the binary variable takes a value of 1, then the flow variable may take a non-zero value. And this can be stated the other way around. That is, if the flow variable is non-zero, then the binary variable will have a value of 1. And conversely, if the flow variable is 0, the corresponding or associated binary variable will also be 0. So let's take a look at how we can use binary variables in some formulations. In three ways: in the objective function, multiple lower bounds, and in summation constraints. So suppose we have this simple problem. We have 3 wells present, and they're subject to certain constraints. And we've associated a binary variable with each candidate well. And because of that, we're now able to change the objective function to minimize both the cost of well operation and the cost of well installation. Without the binary variable, we wouldn't know necessarily which wells would be installed, so incorporating that installation cost would be not possible. With the binary variables present, however, we can write an objective function for this problem that looks like this. Z is the objective function, which we're going to minimize, and it consists of the summation of the pumping rates, as we've seen before, multiplied by a cost coefficient for each pumping rate, and added to that is the summation of the binary variable values with a cost of installation for each well. So the way this works is that if QW1 is selected to operate, the associated binary variable will take a value of 1 there, and the cost of installation of that well will be added to the objective function, along with the operating cost at whatever flow rate is selected for well 1 that will be added to the objective function. We can visualize how this works with the objective function. Those terms are related to the first well, at least. If the flow rate is 0, the cost is 0. If the flow rate takes any non-zero value, the cost immediately jumps up by an amount equal to the installation cost for that well, and then the cost continues to increase in linear fashion in proportion to the cost coefficient on operation of that well. Second thing we want to look at is bound constraints on flow variables. So in a problem without binary variables, GWM allows a lower bound of 0 on pumping and some specified upper bound. But this may present some problems. There may be circumstances where the optimal pumping rate may be impractically small, and what you really want to do is impose a lower bound which is non-zero. But if you explicitly do this, then you've essentially forced the well to operate, which may not be what you want to do. You may wish to see if the optimization algorithm selects the well for operation rather than forcing it to. In other words, what you really may want is to have this idea of two different lower bounds. If the well is installed or if it's operating, then its lower bound is, say, 10,000 units. If the well is not installed, then its lower bound is 0. Or if we write that in constraint form, it would be QW is greater than or equal to 10,000 feet cubed per day, or it's greater than or equal to 0. Using binary variables, GWM allows you to do this. Specifically, if the binary variables are present, and if a lower bound is not 0, as specified in the varcon file, GWM imposes automatically this constraint. And if you study this, you will see that it works as follows. If the binary variable is 0, in other words, if the pumping rate is 0, then the lower bound is 0. We're looking at this constraint. I is 0, the lower bound is 0, and QW can go to 0. If, on the other hand, the binary variable is 1, QW is some value greater than 0, then the constraint is activated and QW must be greater than QW super L, the lower bound. So there we have both of those lower bounds present depending on the value of QW and the value of the associated value of the binary variable. Third thing to examine is binary variables in summation constraints. And here we have an example of directly constraining the number of active wells. So for example, in this with a 3-well problem, we may want to have at least 1 well operating, but no more than 2 wells operating. So if we simply sum the values of the binary variables, for example, in this second constraint, we would see that the sum of them must be less than or equal to 2. In other words, one of them must be 0 and 2 of them can take the value of 1. Similarly, we might want to have a constraint like this, for example, a total budget. So if there was a total budget for the project, we might put constraints on the sum of the operating costs here plus the sum of the installation costs. We'll now turn to the dewater problem and see how we introduce binary variables into the optimization formulation and briefly what the solution looks like. So here we are back in the distribution directory for GWM 2005 version 1-5-2. Going into the data directory, we see the dewater MB problem, which is where the binary variable version of the dewater problem is located. And here we have those files. We'll start with the decvar file. And here it is, and we see the new feature is that we've added 7 binary variables in addition to the 7 flow variables. The binary variables are listed here after the flow variables. The format is each has a name associated with it, a number of decision variables associated with that binary variable. In this case, all of them are 1, and then the actual binary variable that is associated. So binary variable 1 is associated with Q1 and so on. It is possible to have a single binary variable associated with multiple flow variables, which has some interesting applications, which you can see in some of the advanced episodes. We'll now turn to the varchon file and just note that we now have a non-zero lower bound, and this will in fact be implemented because we have binary variables associated with the problem. We now turn to the objective function, and here we have implemented the operating and installation cost concept. So we have both flow variables in the objective and binary variables in the objective. We list the name of the variables and the associated coefficient that shows up in the objective function for those two sets of variables. And finally, we'll look at the summation constraints file. And here we have a single summation constraint, which is the sum of all of the binary variables. The coefficients on those variables are 1, and the constraint says that the summation of all binary variables must be greater than or equal to 3. In other words, at least 3 wells must be active. That's what we're requiring here. And here we have the solution from the GWM out file, and these are the 3 pumping rates that have been selected. And if you compare this with the case without binary variables, you will find that in that case, four wells were selected, and the total pumping was a little bit smaller. We've reduced the number of wells to 3 and incremented slightly the amount of pumping. Also reported here are the optimal values of the binary variables, which of course are associated with numbers 1, 4, and 7, which are the active wells. One more element of binary variables is this problem is solved using the branch and bound algorithm by GWM, which is described in an advanced episode of this series.